Yeah, we get 6 this year. It starts out. Okay, like, let me know. I think, because it's regional to that, JP. Maybe they're just not. I will definitely. I have them people scheduled, so I can just take a picture of it. It's okay.
I do.
Let me go over the calendar, real quick here. So yesterday, we spent the last 2 days, talking about this method. And, today we're gonna be talking about washer method, which is, basically, it's gonna feel like an extension of, this method. It's just that now our shaded region is not going to be flushed up against the axis. There are gonna be some gaps and holes, and we gotta make sure we subtract out the hole, otherwise we won't be getting the true volume of the object. So, the way that we find the bounds, the way that we do either top minus bottom or right minus left, it's the exact same. We just have to insert a second radius, and then pretty much the same formula, just have to extend it a little bit. But we'll spend today and Monday just going over that topic. Okay. Tuesday will be a half day, so afternoon, I think we only have like maybe 20 minutes per class, so I'm not gonna cover anything new, just if the students are here, I'll just continue to do some practice problems, but I'm not gonna expect to cover anything significant on this day, just because it was such a short period. And then on Wednesday, we'll start our final unit, our final topic, which is volume by cross section. The idea there is we're building shapes on top of the base. There's no rotation, but the formula will look a little different, but we'll spend a day on that. We'll spend Thursday on that as well. We can also start our test review, Friday test review, Wednesday test review. So we'll have 3 days to do test review, and then the test will be the Thursday after the break. And after that, we'll begin our AP review. Okay. All right, so let's go to page 13, your packet. Okay, so I'm gonna start off by doing a two-dimensional drawing here and see if we can talk about something that you already know. So let's say we have a circle within a circle. And I asked you to find the area of the region between the two concentric circles. How would you go about finding it? What information will we need to find the area of that region? Yeah, find the area of the entire circle, which means we need to find the what? Radius. So we need to find the radius of the big circle, and then, yeah, find the radius of a small circle, and then subtract the areas, right? So pi big R squared minus pi little r squared. Okay. So if you can understand that, then that's basically what washer method is. Okay. So if you just simply put an integral in front and dx at the end, there it is. That's your, basically we're taking that area of that ring and we're extending it over the course of whatever that shape is. Okay. So if you understand that this two-dimensional version of it, then we just put an integral in front and, and that's our formula. Okay, so that's the big picture here. So visually, let's review this method. So this method, okay, is where we have a shaded region. and an axis of revolution. But look at where the dotted line is in relation to the shaded region. You don't see any gaps, right? This is completely flushed up against the axis of revolution. So when there's rotation, it's going to be a completely solid object. You're not going to be able to put your hand in it. It's just going to be completely filled out. Now, let's say I have a leaf, kind of a leaf shaped object that is pointing at a 45-degree or kind of at an angle. Now, let's say we're still rotating about the x-axis. Okay, imagine this leaf rotating around. We're still getting kind of like a similar shape, but what's different here? There's a gap, right? There's a hole. Now, it's not a complete hole. It's still touching, but you can tell that there's certainly a gap, right? So here's the big picture is that the way you can tell whether, without even looking at the full picture of the 3D image, look at your shaded region in relation to the dotted line. Okay? If it's a flat surface up against the line, it's this method. If it's not a flat surface up against the line, it's Wassermann. Okay, so that's all there is to it. Now it could be touching, but it could be completely off. Right. So if you see any sort of a gap, if it's touching, it's not good enough. Okay, this is not good enough for this method. This is going to be Wassermann method. So if you see any curved region up against a surface, up against the axis, it's going to be Wassermann method. If you see a complete hole, complete gap where it's not even touching, it's also Wassermann method. Okay, so the challenge here is that we're going to have to create two radius, right? Because we have to basically find the volume of the full object, and then we have to subtract out the volume of the inside portion. If we don't, then we're not finding the true volume of the object that we see. Another thing that I want you to point out is that the radius has to involve the what of the circle, both radius has to involve the center, right? Can I put a segment here and call that the radius? I can't, right? So we got to be careful about that because I think the tendency is we're going to want to do this. We're going to want to connect the length between the shaded region and call that the radius. But remember, the axis of revolution is the center of your object. So whatever radius we draw, we have to include the dotted line. Okay, so make sure that whenever you draw a radius, start on the dotted line and extend out. That way you're not going to make a mistake in terms of drawing the wrong radius. Okay, so if you look at the formula here, very similar to what we did from a 2D perspective, right? Big R squared minus little r squared, pi r squared minus pi little r squared. Okay, and then we're going to do the same things before. If it's top minus bottom, if it's a horizontal axis of revolution, we'll draw a vertical radius, which will be top minus bottom. If we see a vertical axis of revolution, horizontal radius, which means right minus left. Okay, so we're going to do this problem now and just do it from the beginning. All right, so example 1. Okay, find the volume of the solid enclosed by the graphs y equals x squared. So y equals x squared is a parabola that's concave up, and then y equals square root of x is the graph that's on top. Okay, revolving about the x-axis. So let's go ahead and draw in our axis of revolution. Right. Notice that the shaded region is touching the axis, but that's not good enough, right? It's not up against a flat surface. There's a gap. Maybe not a full gap, not a full hole, but enough for us to know that we have to rely on the washer method. So the washers are just basically different size rings that we're accumulating from one end to the next. Okay, so we know it's washer method. We know there's a gap. We have to draw two radius. So go ahead and find a spot on your dotted line. Okay, and then you're going to extend to the furthest boundary that you see. Okay. We're going to call that big R. Just like a two-dimensional version of it, right? The one that extends to the further circle is the one that's larger. So that's the big radius. Okay. Again, this looks like the edge of your diagram, but it's really the center of your diagram, right? So after the rotation occurs, right, the axis of revolution is going to be in the center of your object. Okay. All right, so we have big radius figured out. Now let's draw the little radius. So little radius, small radius. Also, put your pen and pencil on the dotted line. And now you're going to extend to the closer boundary that you see. Put them relatively close to each other. If you put them relatively close to each other, it'll be very obvious to see which one is big R and which one is little r, because big R is always the one that's longer. Little r is always the one that's shorter. Any questions? Now, when you find the bounds, and this is important, when you find the bounds, just look at your shaded region. Okay, so pretend like as if you're just finding area. The bounds, the same thing. Okay, so sometimes you may see axis of revolution that's really far away, and you feel like you got to do something different with the bounds, but the bounds is just for your shaded region. You don't care about where your axis is. You don't care about where the object's going to end up looping around. You just focus on your axis on your shaded region. That's all you need to care about. So you're going to find the bounds the same way for area, for volume. By this method, volume by washer method, it's not going to change. You're just going to find the furthest left and furthest right, and then you can find the bounds. Okay, so in this case, this is the top minus bottom or right minus left? The top minus bottom, right? Because we have a horizontal axis, vertical radius, top minus bottom. So that means we have to find our bounds from the left to the right. I think this we can tell was the furthest left x value that you see. 0. What's the furthest right x value? 1. Okay, we're looking at that x value there. Okay, good. So we have our bounds. We know we have that taken care of. Let's build our two radius, big R. We're going to ask ourselves, top minus bottom. Look at your big radius and look at what the top of the radius is sitting on. What's the top of the radius sitting on? What's it touching? The root x, right? So the root x is going to be the top of my big radius, top minus bottom. Look at the bottom of your radius. What's the bottom of the radius touching? 0. So root x minus 0. Which I can clean up to be just root x. Okay, little r. Okay, what's the top of little r sitting on? X squared. Okay, so x squared comes first. Minus 0. Yeah. All right, so now let's build our volume formula. V equals pi depth integral from x1 to x2. We already discovered that our x1 and x2 are 0 and 1. Now the formula says big radius squared. We have to square our radius separately. We can't say big R minus little r and then square the whole thing. We have to square them differently, right? Just like how you did it with the two-dimensional figure, right? You did pi r squared minus pi little r squared. Same idea. We have to square the radius differently. Okay. Any questions? Okay, so as we do more of these problems, our radius is going to get messier and messier. So my suggestion is in your calculator that you enter your R1 and R2 under separate Y1s and Y2s. That way, when you enter things into your home screen, it'll look nice and clean, and you want to deal with a bunch of parentheses and messiness. You can kind of separate that out. So I'm just going to put the radius in. So big R is square root of x, and I'll put that under Y1. Y2, I will have that called x squared. Go back to your home screen by doing second mode. Math 9. Leave pi out of it. We're just going to go from 0 to 1. Big radius, that's stored under Y1. So I'll do alpha trace Alpha trace will give me a list of menus. I'll do y1, make sure you square. Minus alpha trace, y2 is holding my little radius. Square that, dx. Also, the nice thing is, once you have this down, then if you have further washer methods that you want to do, you can just go back and change your y1, y2, recall this again and change your bounds, and you can just do your problem without having to re-enter all this again. Okay, math fraction, this will get me 3/10. That's the volume of this bowl. And I have to make sure I include what at the end? Pi. You could, but we want to kind of leave our answer as exact as possible. So typically we leave that pi there. But yes, if you wanted to find a true three decimal place approximation of your volume, then you could multiply that pi through. Typically, from what I see on AP exams, they leave that pi attached, or they leave that pi showing. But if it was a calculator question and your multiple choice all had just decimals in it, then you would multiply that pi through and see if you can find a match that is the closest. The two biggest issues that I see that students make with washer method, one is the formula, memorizing it incorrectly. Sometimes students, they want to just subtract the big R, little r together and then square just all at once. So we gotta make sure we square them separately. Okay. The other issue that I see students make with washer method is they would connect between the shader region and call it the radius. Okay. You can't do that. Okay, so I know we do that for area, but not for washer method. For washer method, if we connect these two, we can't call it the radius because the radius has to involve the center of your object. So make sure that both your radius are extending from your dotted line out to your two different boundaries. Right. So that's the biggest issue that I see with washer methods. Okay, let's look at example 2. Okay, find the volume of the solid created by revolving the function y equals x squared plus 1. That's a parabola with a y-intercept of 1 that's opening up, bounded by the line y equals 2, revolved about the x-axis. Okay, so we have the two graphs here. That's going to create our shaded region, but then our rotation is along a different line. Okay, so here's y equals x squared plus 1. There's my parabola, y equals 2, that's a horizontal line. Okay, so there's my shaded region. I'm going to rotate it around about the x-axis. The x-axis, what's the equation for the x-axis? Y equals 0. Okay, do you see a gap between the axis and the shaded region? Yes, so there's a hole, and so it's going to be washer method. Now, let me extend something here before. What if the dotted line was here? And I'm rotating around this dotted line, around y equals 1. Washer disk. Still washer. Why is that? It's touching. I know it's touching. But there's still a gap, right? It's not a flat surface, right? The shader region has to have a flat surface up against the dotted line if we want to do this method. So really, with this shape, there's only one place that you can have it and be this method. Where is it? Y equals 2. This is the only place that with this shape, you can have this method. Everything else has to be washer method because there's no other flat surface, right? So you gotta have a flat surface if you want to do this method. Washer method is basically anything else. So it's very, basically, this method is very restrictive, right? If you don't have a flat surface, it's not gonna be this method. Okay, doesn't matter if it's touching. Okay. All right, so we know it's washer method. We know how to draw two radius. So again, every radius you draw has to start on the dotted line because if you can imagine, it's gonna be kind of like a funny ring-shaped object with kind of like a curved inside, right? Okay, so you can place your pen or pencil anywhere. I'm going to extend to the furthest boundary that I see. And I'll call that big R. Yeah. That's not going to happen because as long as you put your two radius next to each other, okay? If you put them relatively close to each other, the longer one will always be big R and the shorter one will always be little r. Okay, if you put them too far apart, then the graphs may suddenly change in a way where little r may look longer than big R. So yeah, my suggestion is put them relatively close to each other. That way the graph won't have no chance of changing too much and the big R will always be longer. All right, any questions here? Okay, so let's build our big radius. Oh, I'm sorry, we should find the bounds first. So the bounds, we can't really tell by looking at the graph. So what can we do to find these boundaries here? Good, we set the line equal to the curve. So I have y equals x squared plus 1. I have y equals 2. I'll set them equal to each other. Subtract 1 from both sides and then take the square root. So x equals plus or minus 1. Okay. So x equals 1, x equals negative 1. Those are my two bounds. Okay, I'll come back to that when I'm ready for my volume formula. All right, so big radius, the longer one. Let's look at the top of big radius. What graph is it touching? The 2. Look at the bottom of the big radius. What's that touching? The 0. Okay, so big radius does not see the curve at all, right? It's just the line and the x-axis. Okay, little radius. Look at what the top of little radius is sitting on. Sitting on the what? X squared plus 1. Minus, what's the bottom of little radius sitting on? The 0. Okay, everything that we need is in front of us. We just put it into our volume notebook, right? Okay, pi integral from -1 to 1. Big radius squared minus little radius squared. Okay, put your big R and little r in separate y1 and y2s. That's my suggestion. You can enter it all in to this home screen at once if you like, but this is how I like to do it. That way I can just scroll up and use what I've already entered, and the only thing I need to change are the bounds. Okay, questions so far? I want you to try the next one because I feel like it's very similar. And then we'll look at example 4 where the vertical axis, we got to do a whole bunch of changes, but I think this next one you guys can do. Yeah, example 3. Go ahead and try example 3. Around the y-axis. Okay, so that's only it's only gonna be half the diagram. It's not very clear. Let me. Okay, one goes x plus 1. Okay, it says and the y-axis, so it's only going to be half. You can choose either region, they're symmetrical, but bounded by the y-axis, bounded by the curve, and bounded by the line. Okay, there we go. Just that region there. Okay, so we see an obvious gap. This is going to be washer method as well. Top minus bottom. Sometimes your axis is on the top, sometimes it's on the bottom. You just follow whatever the graph has for you. Okay, are we able to draw the two radius? Okay. I think the intersections we already can figure out from before, right? What's our bounds going to be? Left to right, 0 to 1, right? We found that from before already. Okay. All right, let's build our radius. Top minus bottom. What's the top of big radius sitting on? Let me label them. Okay. I have big R on the left and little r on the right. Okay. What's the top of big R sitting on? 4. Good. What's the bottom of big radius sitting on? X squared plus 1. Okay. Now I'm going to write this out here. Tell me what you see. Is that okay? What's wrong there? Parentheses, right? If you write it that way, you're going to write it out combine as 4 plus 1 instead of 4 minus 1. So careful with that. Careful with the parentheses. Okay, look at the location of your little r. What's the top of little radius sitting on? 4. Okay, what's the bottom of little radius sitting on? The 2. That's it. Do you guys get 3.2? Or 16/5? Okay. So we're good with top minus bottom. Let's look at example 4. Find the volume of the solid created enclosed region, y equals x squared, y equals square root of x. Same shaded region as what we solved for example 1, but revolving about the line x equals -2. It's over here. Okay, disk or washer method. Washer method. Actually, with this shape, is there any chance that we can do any disk method with this shape? Right, there's no flat surface, right? So no matter where we put our axis, it's gonna have to be washer method no matter where it is, even if it's touching. Okay, so I think what I see students struggle with is they say, oh, it's touching, so it should be this method. Not the case, right? You only do this method if it's up against a flat surface of your shaded region. All right, so what's also another challenge with this problem? It's a vertical axis, which means right minus left, which means our equations are not in the proper form, right? We've got to take the time to rewrite all of our equations. None of them are, this is ready. The x minus x equals -2 is in the proper form, but not these equations. Okay, let's go ahead and draw the radius first, though. Okay, so you're going to start on your axis. I know also another a strange thing that I see, it feels like this is the edge of the diagram, right? But this is going to be flipped over on this side. So it's going to be kind of like this weird lampshade looking object, right? It's all the way over here. So I want to keep reminding us that this is not the edge of the diagram. This is the center of the diagram. So we never want to draw the radius this way. I always want to include the axis. Okay? So from the axis, you're going to extend to the furthest boundary that you see. From the axis again, you're going to extend to the closer boundary. We'll do right minus left once we've adjusted our equation. So let's do this one first. This curve is what? The y equals x squared. But I need to solve for what? X. So to solve for x, I can take the what? The root. Now there's two of them, which are two equations here. Which one do I want to use? This is on the positive side, right? So positive root of y. Okay, let's look at the one that's on the inside. Initially, it's y equals square root of x. So I can also write square root of x equals y. But I want to solve for x. So what can I do to both sides? Square both sides. So x equals what? Y squared. Okay, now we're stacking these circular rings from the lowest to the highest y value. What's the lowest y value that you see? 0. What's the highest y value that you see? 1. Okay. Let's build our two radius, big R, Y. Okay, now we're doing right minus left. Let me label them again. The big R is the longer one. Little r is the smaller one, smaller length. Sorry, Y. Okay, so let's look at our big radius here. Let's look at the right endpoint of the big radius. What graph is it sitting on? Yep, square root of y, that comes first. Minus, what's the left endpoint sitting on? So we got to change it to a what? Y is it y square root of y minus 2? Good. Gosh, just be careful about that. This minus is different from the minus from the axis, right? So ends up being a plus. All right, little r. What's the right endpoint of little r sitting on? On the y squared. Minus, what's the left endpoint sitting on? -2. All right, that's the hardest part, right? If you build your radius, get your bounds, then everything is just easy because you just put it into your calculator or into your formula. Make sure you're squaring your radius separately. On paper, I want to see y's, but in the calculator, you're going to have to enter in x's. Okay, calculator have root x plus 2 and x squared plus 2. Doesn't convert to a fraction, it's okay. I'll just write it as 3 decimal places, include the pi. Units cubed. Okay, let's see if we can try 1 or 2 more. Let's go into the next page. This is the page 15. I have everything drawn for you here. Let's see if we can get through A and B. Top minus bottom and the right minus left. Any questions here? Okay, keep reminding yourself your axis is the center of your object, even though it looks like the edge of your diagram. Right? This is going to end up rotating all the way around 360 degrees around that axis. I know that I have all the axes labeled, but let's say I didn't label it for us here. How would you find, because you know the left bound is 0, but how would you find that right bound? That equations equal, right? You have the y equals 1 and root x minus 1, set them equal to each other, solve for x. Top minus bottom is usually not what we find challenging. It's the right minus left, right? Spending the time to make sure our equations are in the proper form. So see if you can try part B once you're good with A. Yeah, careful with that -3, right? That -3 we got to carry over. Ends up being a plus between the two terms. Okay, try part B. I will work through part B from scratch, but want to leave this up on the board. Make sure you guys are good with A. Okay, does anybody still need part A? Washer method and vertical axis. We need two radius, one to extend to the curve, and one that extends to the y-axis. Well, the x-axis is easy because we know that's just x equals 0. But the curve is not in the proper form. We know it's going to be, we know it's root x minus 1 equals y, right? That's the equation that's given to us, but we have to solve for a different variable here. I think the bounds is easy as well. Can you tell what the bounds will be? -1 to, what's the y value here? Yeah, 1. Okay, yeah, -1 to 1. Okay, right minus left. We look at the right endpoint of the radius. It's sitting on the y plus 1 squared. Minus what? Yeah. Gotta change that sign, right? Because we have two negatives there. Okay, little r. What's the right endpoint sitting on? 0. 0 minus -1. Okay. All right, you guys have homework from 7.2b for washer method. Nothing new on Monday. We're just going to practice more with this. Okay. All right, come get your phones. Yeah.
Okay. My question is for this.
Yeah, it says bounded by, the Y axis. So, in these three, these are boundaries. So it's only gonna be half the way. So if I didn't include the boundary, that's what it would be. But I think I would be more specific to say response. Like right now, it does feel like. In this case, it didn't matter because they're symmetrical, so it could be not the same, we're gonna say that. But I mean, I would specify it.